Okay, so one last example, and that is to redo this problem for the electric field of a disk, not thinking of the disk as being made up of an area that we integrate over, but thinking of the disk as being made up of a series of rings nested inside of one another. And this is the way your book does the example. So the way I did the example was a little more complicated than the way your book does, but it's actually really nice to see it done both ways. We already, a few examples ago, found the electric field of a disk of radius a that we're a distance x away from. And that looked like this, 1 over 4 pi epsilon naught, the total charge of the, of ring. Let me say that again. We already found the electric field of a ring of radius a distance x away, is equal to this, is equal to the charge of the ring times our distance from the ring, divided by square root of x squared plus a squared, where a is the radius of the ring, to the 3/2 power. We're going to use this as our dq. In other words, we're going to think of this disk as being made up of a bunch of rings, and we're going to add up the electric field of all of those individual rings to determine the total electric field. So the electric field due to this disk is going to be equal to the integral over dE, where dE is the electric field of a ring. One thing to note is we do not have to worry about components and cosine thetas here, because we already did that to find the electric field of the ring. In other words, this is already the electric field in the positive direction due to this ring of charge. So all we have to do is add this up for a bunch of infinitesimally thin rings, and that will give us the total electric field. The tricky part of this is expressing dq of the area of the disk in terms of this charge of the ring. We can write that the little bits of charge are equal to sigma times dA. If we're thinking about this in terms of a disk with a particular area. But how do we write that if we're thinking about it in terms of these little rings? Well, if we think about each of these rings as a bit of area, before we were thinking of these rings as infinitesimally thin with no thickness whatsoever, but now we're imagining, that's not very good, let me try that again. Now we're imagining each of these rings as having a tiny thickness dr. Right? So the ring, rather than being infinitesimal now, actually has a tiny, tiny, tiny area. So we can write that the area of this ring, dA, is equal to the area of this is 2 pi r dr. Okay, the area of that little slice of the disk is equal to the circumference of that ring times dr, the little bit of thickness. So when we write our electric field is equal to the integral of dE, which is equal to, we have to translate this expression here of the electric field for a ring in terms of the variables for our disk, which are a little bit different. So we have to be really, really careful here. In this expression, the electric field of a ring, x was the distance from the ring and a was the radius of the ring. Here, we're using z for the distance from here to here, and we're using r as the radial variable from the origin out to our each individual ring. So this is going to be equal to the integral of 1 over 4 pi epsilon naught. Instead of q, we have dq. Instead of x, we have z. Our distance from each ring is z in this new coordinate system, over z squared plus, and the radius of each individual ring is r, so r squared to the 3/2. Okay? And now we have to rewrite that in terms of sigma, in terms of our area charge density. So dq, let me change colors here for a second, dq is equal to sigma dA, right? The charge density times, the charge is equal to the charge density times the area, and dA is equal to this area of this little ring, which is 2 pi r dr. Okay, so this integral becomes what have we got? 1 over 4 pi epsilon naught can come out front, times the integral. Z is actually a constant, that can come out front too. Our distance from that ring doesn't change as we integrate outward. Sigma times 2 pi r dr over z squared plus r squared to the 3 halves. And what's our integral now? Our integral is we're integrating all of these rings from an infinitesimally small ring at the origin out to a ring that encompasses the entire disk. So the limits of integration on r are from r equals 0 to r equals the total radius of the whole disk. So that gives us, what have we got? We've got z times sigma out in front. That 2 pi cancels that. It gives us 2 epsilon naught out front, times the integral from 0 to capital R of r over z squared plus r squared to the 3 halves dr. And now we've gotten it to the exact same point we had it in the last video. We should recognize this integral is the same integral we had before, and so we will get the same answer we got before, showing that the two agree. So what we should learn from this is that this integral is actually way easier to set up in this example than the integral we did before. So sometimes when you have a problem where you're integrating to find a shape, you can make that integration simpler by taking advantage of shapes that you already know the electric field of. In this case, we already know the electric field of a ring, so we can build other shapes out of rings in order to find electric fields of those shapes. Now that we know the electric field of a disk, imagine you were given a problem, say, to find the electric field of a cylinder. Okay. Suppose you are a distance z away from a cylinder of radius r and height h. How would you find the electric field? Well, you could integrate over the three-dimensional volume of that cylinder, which would be fairly complicated, involve three-dimensional coordinate systems, or you could just recognize that a cylinder is just a stack of disks on top of one another, and you could find the electric field due to one of these disks using the answer we just got from this problem, and then add those disks up from top to bottom in order to get the electric field of the whole object. So we'll see a few more examples of this as we go on, and I may give you some homework. In fact, I might give you that cylinder problem as a homework problem, just to see, just to give you practice in setting up these integrals. So I'll go ahead and stop there for today and for this week entirely. I'll put some homework problems up on Canvas. And then next week we'll get into chapter 22 and Gauss's law.